my name is Lillian Wilson-Wade, and this is Lab 5, examining Faraday's Law. In this lab, we will be exploring Faraday's Law by observing a powerful magnet being dropped down a conductive non-ferrous tube and falling out of the other end. In this lab, the procedures involve collecting observational data of that magnet falling through the tube of foil, modeling that magnet-tube interaction computationally, and then comparing our computational predictions with the observed data. From my experimental results, I found it took the magnet approximately 1.27 seconds to fall through the tube, and from my computational model, I found it took the magnet approximately 0.98 seconds. Let's go over some of the key concepts to understanding this lab. First would be the computation of a magnetic field of a dipole, which we find through the Biot-Savart law. Next, obviously, a big principle in this lab is Faraday's law. Faraday's law states that a time-varying magnetic field can produce an EMF that can induce current. In this lab, the source of the external magnetic field was the bar magnet, and the induced current wraps around the aluminum foil tube. It's really important in this lab that we use a non-ferrous tube, as stated previously, because any tubes with iron would have some sort of ferromagnetic interaction that will affect Faraday's law. Additionally, we'll be utilizing Newton's second law to update the position and velocity of the modeled magnet in the computational model, and Newton's third law will help us calculate the force on the magnet in the loop. Let's go over the procedures in this lab. So to begin this lab, I marked the north pole of my magnet using the magnetometer app. I held the tube foil vertically and positioned the magnet at the top opening with the north pole facing downwards. Using my smartphone, I recorded the entire length of the tube with my camera and dropped the magnet through the tube. I scrubbed through the video I recorded to calculate the time it took the magnet to fall through the length of tube and repeated these procedures 5 times to calculate the average time it took the magnet to fall. On the right, you can see some of my recorded data. From my 5 trials, I found it took approximately 1.27 seconds for the magnet to fall through the tube completely. I also recorded the length, width, and radius of the aluminum foil tube along with the mass of the magnet, and I also utilized the magnetic dipole moment I calculated previously in Lab 3. Now let's review the computational model. I began by setting up the geometry of my tube, then the geometry and visualization of my magnet. I then set up a function to calculate magnetic field utilizing the code that we put together in Lab 3. I then set up a function to calculate the change in flux over time through each ring of the tube due to the falling magnet. I then created a simulation loop to visualize the motion of the magnet in the tube, calculated the current on the ring in this loop. I also calculate the magnetic field on each ring, then calculate the net force on the magnet and update the magnet's position and velocity and iterate until the magnet is at the end of the loop. From my model, you could see my results. My simulation stated it would take approximately 0.98 seconds in the tube for the magnet to go from the top to the bottom. Now to answer some questions to interpret this simulation. So the intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions, so which color corresponds to which direction. I found that red corresponded to clockwise and blue to counterclockwise. What happens to the dynamics of the system when you flip the magnet around? We would observe the same motion but with a flipped current, so same magnitude but opposite sign. How does the total time in tube of your real-world system compare to that of the computational system? How might the computational system be made more accurate? In our real-world model, air resistance and conductivity resistance are present, so our computational model is going to be less accurate because we don't account for those factors. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The slope of the velocity versus time plot is always negative or 0. When it's negative, we can infer that the gravitational force is the sole force acting on the magnet going downwards. When the slope is 0, the magnetic force is actually present and our net force equals 0, which ensures that velocity is constant. Now to answer some additional final questions, what if the resistivity of the conductor were reduced as close as possible to 0? Well, if the resistivity of the conductor were reduced as close as possible to 0, the induced current would be increased because the two are inversely proportional. The magnetic force would then grow to magnitude and the magnet would have fallen more slowly because the magnetic force would greater counteract the gravitational force. What if holes or slots were cut into the tube? Well, then in that case, the magnet would fall faster, because if holes or slots were cut into the tube, the cylinder would contain less rings, or less hole rings, and thus there would be a weaker magnetic force on the magnet. Thank you so much for listening to my Lab 5.